and my talk is about type-safe dependency injection in reactive applications. So just a few words about me. I am from Poland, from Krakow, where we have an active and big Scala community and user group. And I also work at Ocado Technology. We are an IT company building a variety of services and solutions for online shopping and grocery. And of course, we are using Scala vastly in lots of our projects. So today, I would like to tell you something about a compile-time dependency injection technique for reactive applications, which is implemented for Akka and makes use of Scala type system to provide functional and type-safe dependencies injection mechanism for Akka actors. So I would like to tell you what kinds of problems I had with asynchronous and dynamic dependencies in Akka actors, and also why I needed to refactor it, and why I had to come up with a special type of dependency injection. And of course, I will show you how I approached it and how I solved this problem with Scala, its powerful type system, and also more specifically with Shapeless. So this is also going to be a case study of refactoring and designing with type-level programming in Scala. So to demonstrate the problem, I have prepared a simple domain. So here we have something basically kind of an online shop. So the rectangles are some domain types like basket, shop, users, and so on. And at this image, the arrows show the flow of dependencies in this domain. So what's important here about the dependencies is that they are going to be asynchronous, dynamic, so that may be futures, or messages from other actors. So we have here this one star icon, which is an Akka actor. So another kind of asynchronous dependency may be a message sent from an actor. So most generally, the kind of dependencies I am going to talk about are some dynamic asynchronous values that actors can obtain, get at startup, and then they can just use it. So that may be, for example, some values, data from other external services, but maybe also some messages from other actors in the same application. So now, let's say that we are going to introduce a new actor, which is going to require and work on objects of two types, so those two red rectangles, so promotions and products. But while we are starting this actor, we have two values available, so of those green types, the green rectangles. So when we implement an actor, we have to use the knowledge about the flow of the dependencies to get from green values to the red values. So we have to obtain the dependencies. So how can we do it in Akka? So the future dependencies are just some functions from some parameters, from some attributes, to future of something else. So here we have three kinds of such dependencies, which may be function from shop ID to future of shop, another function from shop to future of promotions, and another one in the top, which is a function from user and shop to future of basket. And of course, each of those functions must be somewhere available for us. So we have just some names. They can be provided for some service objects or something like this. So then we also have, of course, a reference to this basket actor. So now we have basically all the stuff we need to create and implement an actor. So what we can do is just to pass all this stuff into the actor class, and we can implement an actor class like this. So it looks a bit ugly, and this is how it might look like. So basically, we have an actor class which takes all these parameters. So the known values, some functions, returning futures, maybe some reference to an actor. And then we have to start this actor with composing all the dependencies together to make the actor working, to configure it properly. So we have basically two ways to do it. As we have some future functions, we can compose the futures, for example, in pre-start method. So in Akka, pre-start is a function which is just called just before the actor is started. So here we can use for comprehension to run a few future functions. And finally, we can, for example, assign the result to a private var. Then we can also use something like a state machine in Akka, we have become method which changes the behavior. The behavior is defined by receive block, which is just kind of partial function from type of message to some action. So we can just go through a few behaviors in the state machine, which is our set of configuration steps. So we are waiting for some message, we are sending something else, and this way we receive and obtain all the dependencies as future values or as messages from other actors. And finally, we change the behavior to this one final function, which really defines what this actor is going to do. So the whole responsibility of this actor is this one simple little receive block. So all the other code is some boilerplate. So we can also imagine that if we have other actors in the same application, they may do similar steps. There may be a lot of duplication. And there are also other problems like, for example, unnecessary mutable variables like the one with promotions. So what we would prefer to have here would be just an actor as simple as here. So as it requires only values of two types, we would like to pass them as parameters. And then we can explicitly focus on the real behavior of these actors. So we can get rid of all these pre-configuration dependencies fetching phases and implement an actor directly. So to do this, we have to somehow provide the dependencies for the actor from outside. So we can first try it with just composing the futures. So let's say we are just in the place where in the application the actor is started. So we have a few future functions. So we can take them and compose in for comprehension. But we have also this one kind of dependency, which is based on exchanging messages with an actor. So for this purpose, in Akka, we have ask pattern, which is this question mark, and it allows us to send a message to an actor and expect for the result as a future. So in this case, we send a message, which is constructed from basket value, and we map the result to products so that we get another future with type products. So this way we have 4 futures. We can compose them in for comprehension. And finally, we yield Akka props. So props is just something like a wrapper for constructor, which tells the actor system how to start this particular actor. So this is just something similar to constructor. So of course, this whole expression still is a future. So at this point, we can introduce something like a proxy actor. So the proxy actor could take this future as its parameter and wait for the result of the future inside. And once the result is ready and succeeded, it can create our real target actor as its child and can start forwarding the messages to the real actor. So this way, the proxy should be visible from outside as a normal actor, and its presence should be transparent. So the benefit is that here we get an actor reference directly in a just blocking way. And we have the reference immediately. But now we have some problems. We are using for comprehension, which just uses monadic flat map binding. So this makes the futures running sequentially. So if we have, for example, this find promotions function, it is dependent on value shop, which is already available 2 lines above. But because it is just a sequence of flat map calls, this find promotions function has to wait for the one intermediate result basket, so a value which it is not dependent on. So in fact, all the futures are running sequentially. The same case here, of course. So it's not very efficient. And of course, we can deal with it. We can refactor it to compose the futures in a better way outside. And then also yield our props as another future. So we can do it, but it requires some extra effort. And we can often still introduce some other bugs later. So it just requires us to focus on this extra thing. So at this point, the API of such solutions, so generally the approach may not look very good. And it may look even worse because we would have to extract composition of futures outside to run it more efficient. So I started to thinking about how it could look, how convenient DSL and API could look like. And my idea was something like here. So this is just a beginning design and idea how it may look like, so how the API could be built. So what we have here is first the proxy props class. So this class, to be constructed, takes as parameter a function. This is a function from some attributes, any kind of attributes, to akka props. So this is a class which tells us how our actor is going to be created, so what it requires. So the parameters of this function here inside tells us what are dependencies for our actor. So then, having the proxy props, we can apply it to some dependencies. Dependencies are built with something like a Fluent API, which has two kinds of methods, which is given and requires. The given method can just take just pure values, which are already known, so like the shop ID and user in our case, so those two green values which are already known at this point. And the other kind of method is requires, which generally can take, for example, a function from some attribute to future of something else. So it takes a function, and based on this, it can see what this function requires, so what are the parameters, and what it produces. So based on types, it is going to compose this function with the previous already known dependencies to produce another one. And the second version of requires method is for dependencies requiring exchanging messages with actors. So it takes an actor reference, a function creating the ask message, the question to the actor from some parameters, and the class of expected result. So now we can also wrap the parameters of requires function to additional classes so that we can now extract it outside. So we have future dependency and actor dependency, so just two types. And it allows us to unify requires method so that it always takes just one parameter. And also the dependencies can be defined outside in a declarative and functional way. So this is how it is finally going to look like. So this is the desired API. So now what could we expect from this kind of solution? So the first thing is that we would like the compiler to check availability of dependencies in compile time. So when we have our proxy props, it has some requirements which are known by types. So while providing dependencies for the proxy props, the compiler should check that we are providing exactly the dependencies which are required for this actor. And the second thing we would like to have is more efficient futures composition. So as opposed to for comprehension, we would like the futures to be run really parallelly and not in a sequential way. Okay, so as I told you, it is going to be type safe and type driven. So I would like to tell you more about what the types of the classes here are. So first we have this dependencies class. So the purpose of this class is to retain all types of all dependencies it will hold. So it has to be generic enough to remember all types it can contain. So first we just create empty dependencies, so it doesn't have anything yet. But then we start using given method. So first, of course, it has to remember type shop ID. So it may look like being parameterized with shop ID. But then we use given method another time. And this time, the dependencies class has to retain both types, shop ID and user. So now it's becoming something like a tuple, a pair. But then, of course, we are using the requires method, which adds additional dependencies, and so on. And finally, we end up with something like a tuple of size 6. So this is something the dependencies has to retain and remember in compile time to have the information about all dependencies. But of course, Scala tuples are not generic enough. And we can just take any tuple and say that we want to return also a type tuple, but extend it by one more additional type. So this is where Shapeless comes with help. Who has heard about Shapeless? And who has used it? Okay, so not so many. So Shapeless is a Scala library for generic type-level programming, and its main concept is heterogeneous list. In short, an HList. So an HList is a list which can retain types of all elements it contains. So in this case, we create an HList with element of type int, string, and then list of int. So if we take head of this list, the compiler will be aware that the type of this element is exactly int. Then we can take another second element here, and still compiler knows what is the type. So this is a string. And the same, of course, for the last element, which is list of int here. So compiler knows exactly what is the type of each element. But if we try to take, for example, another next element, then as opposed to Scala lists, it will fail not in runtime, but in compile time. So this code will not compile because HList both knows what are the types of elements. So by the way, it also knows how many elements it exactly contains. So this is possible because of recursive type definition. So the HList is a trait which has two implementations. The first one for empty list, which is case object HNil, so similar to Scala list, which has just a nil. And the second implementation is this case class double column, which is implementation of non-empty HLists. So it is parameterized with two types. The first type is type of the head, and the second type is the recursive type declaration of the tail. It is upper bounded by HList, of course. So this is the recursion here. We have a type of head and the type of the tail. So if we define an HList like in the example before, we have an HList with int, string, and a list. So if we take a look at the type, it will be this non-empty HList case, so the double column class. So the first parameter will be int, and the second parameter is another HList inside, which has once again a head and a tail and so on. And the last element always has a tail of type HNil. And of course, we have also a syntactic sugar for that, so this is the line below, so this is just simpler to read and follow. Okay, so now we're back with the dependencies class. So of course, instead of tuples, we can use HList here, which is generic and flexible enough for this case. So we can just extend the list of dependencies, list of the types, while using each method one by one. Then we also have the class Proxy props. So it is created from a function. So this is a function from some parameters, so function of any arity, basically. And it creates always akka props. So in this case, this is a function taking two parameters, promotions and products. So here also we can reflect it in a generic way as a class parameterized with another HList. So in this case, we have two parameters. So we have an HList with promotions and products. And the application of proxy props to some dependencies gives us just akka props. So already an akka provided class which lets us start an actor in the actor system. Okay, now we also have the dependencies definitions. So basically there are two types, future dependency and actor dependency, and each of them is parameterized with two types. The first type is a generic any kind of tuple, and it is the set of requirements for this dependency to be built. And the second type is the produce type. So, for example, if we have a future dependency built from a function taking as parameters user and shop, this is the second val, then the first parameter becomes a tuple of size 2, so a pair with user and shop, so exactly the parameters of the function. Actor dependency is a bit similar, but as the requirement, we take the arguments for the function creating the ask message. So this is the second parameter. So this is the function which requires some parameters to create the message to be sent as our question. So this is where the first parameter for actor dependency comes from. And the second parameter for all dependencies is always just the produced type. So in case of actor dependency, it will just be the class we explicitly pass as the produced type of the dependency. And indeed, the actor dependency is just a subtype of future dependency, so it's just a subclass. Also, under the hood, it just runs a future with akka ask pattern, so it's very similar. Okay, now I would like to focus more on how we build the dependencies. So how exactly they are constructed in compile time. So the dependencies class doesn't run any futures while building it. So it only constructs flow of computation for our futures, but it's completely lazy. So while building it, we don't run any futures. When we want, we call a special method which can run the futures for us. So this will be just lazy, and this is just an abstract flow and graph for futures computation. Okay, so first we create just empty dependencies, so there is nothing yet there. So this is just the empty HList, so the HNil. And then we use the given method. We pass a value of type user, so the first dependency will become a user, more specifically a future of user, because we want all dependencies to be futures, so also the given known values must be wrapped to successful future just for unification with other dependencies. Okay, then we use given method second time. Now we are passing shop ID. So then the dependency object will be able to retain both types. So now it will keep an HList of future with shop and with user. Okay, now we are starting to use the dependencies, so future of actor dependencies, which must be produced by type from some arguments to a produced type. So the first dependency is shop dependency, which requires shop ID and produces shop. So it just wraps a future function from shop ID to future of shop. So at this point, compiler has to do three basic things to check that this code is valid and that it can be compiled. So the first thing is that Shapeless allows us to use any tuple as an HList. So basically Shapeless provides generic conversion between both, so we can use them basically interchangeably. The second thing is that compiler must ensure that shop type at this point mustn't be present in the previous dependencies. This is important because if we want it to be type-driven, the types mustn't be duplicated. Because if we, for example, now duplicate the shop type, then we would have two values with type shop. So if we want to compose it with another dependency later, the second dependency wouldn't know which one of the shops to choose. So for the purpose of type-driven composition, the produced dependencies must be unique. Okay, and finally, to build our new dependency of type shop, of course, the future with shop ID, so the requirement, must be found in the dependencies list. So basically, the compiler has to go through the list with the dependencies and ensure that the type of future of shop ID is present there. So if it is, it can take this particular future, and using the function provided by the shop dependency, it can just use flatmap function to bind it with this function, and it can produce just another future with shop. So in this case, we get a new dependency, which is a future of shop this time. And then we have another dependency. So this is a bit different. Of course, the generic implementation is the same, but it is a bit more complicated because now it requires two types. So it has two requirements, which is user and shop. So now it is different because at this point, compiler has to go through the HList and find two futures. So it has to filter out those two requirements. Now it is important because it allows us to implement efficient futures composition. Because let's assume now that the future of shop ID during runtime is still running, then because of the proper filtering out the correct futures, we are able to ignore this one running future and compose only those two which our new dependency is dependent on. So this way, compiler is able to filter out a new HList with future of user and future of shop. And then, having such an HList, we have to do one additional operation, which is just something like a sequence method, which you have learned about at the previous talk. So it can just convert a list, in this case HList of futures, to one future with an HList. So this is what we get as the result. A future with this particular HList, with user and shop. So having already the user and shop, we can bind it with the function provided by our dependency. So it wraps a function from user and shop to future of basket. So here, having the HList of user and basket, we can just bind it with our dependency, and as a result, we get another future, which is future of basket this time. Okay, now we have two more dependencies which don't differ. So basically, they have some requirements, some produce types. So compiler just goes through the previous dependencies and bind by types the new dependency to previous values. So this way, we get another dependency with promotions, then a new one with products, and finally, we end up with a dependencies object, which is of type dependencies parameterized with all the types of dependencies. So this way, our dependencies object is able, in compile time, to remember and retain all types of dependencies we are using. Okay. We also have this proxy props. So as I told you, it is parameterized with the required types, required parameters for our actors. So this is an HList with our two types, promotions and products. So now we want to apply these proxy props to some dependencies. So to the dependencies we have just built. So of course, at this point, also compiler has to verify that this is valid and legal. So basically, as it requires promotions and products, the compiler has to go through this list and check and ensure that those two types are present there. So only if it's true, the line of code will compile. So in this case, of course, it's valid. So it's okay, and as a result, we get just the props, so the akka provided class props. So this is already a value we can use to start the actor in our actor system. So this starts the proxy. So the proxy is also an important idea here, because the proxy just takes the dependencies and runs them as a future. So it awaits for the result of the dependencies, and once the dependencies are ready and completed, it can start our real target actor as its child. And then it can start forwarding messages to this child actor. Also, if any of the future dependencies fail, then the proxy can retry fetching all dependencies once again, as many times as we want. And if, for example, our target actor is terminated at some point, the proxy can once again try to reconfigure the actor and refresh the dependencies. So basically, from outside, the proxy should be visible just as our normal actor, and the presence of the proxy should be really transparent for us. Okay, and I have applied Shapeless here, which allowed me to design and implement clear and concise API and DSL with reusable and declarative definitions of asynchronous dynamic dependencies. And also the full types awareness allows to implement efficient asynchronous computation. So we can just compose the futures in the most efficient way so that they are not sequential anymore. And finally, the compiler ensures the correctness of our dependencies, so it verifies that we are providing exactly the dependencies that our actor requires. Okay, now I have just a little bonus, so something additional. I would like to explain you a bit how Shapeless works. So for now, I was just telling you on quite high level what the compiler can do, and that it is able to go through the list, check something, filter out something, and so on. Now I would like just to explain it a bit. So as HList is defined recursively, also the logic for HList can be implemented through implicit functions, which requires some recursive implicits of the same type. So let's see how it works on an example. So we have a trait not in. It is parameterized with two types, any type T and type L upper bounded by HList. And this trait must tell us that the first type T is not present in the HList. So we have to implement two implicit functions for this. So of course we will place them inside the companion object of not in, so in the default place where compiler will try to find them. And the first case is just a basic case for empty list. So we have a function which tells us for any type T that this type is not present in HNIL. So it's obvious, so any type is not present in the empty list. The second implicit function is a generic case for non-empty list. So this is the function where we will use the recursive implicit lookup. So on more high level, we can define what it means to be not included in a non-empty HList. So basically it means that our type, T, is different than the head. So this is the first condition. And the second condition is that recursively, it also mustn't be present in the tail of this list. So this is what we have here. We have two type parameters, our type T, and also two types defining the HList. So this is the head, H, and the tail, L. And we produce a not in instance parameterized by T and the HList constructed from those two types. So to apply this function, compiler has to find other implicits. So the first one is to prove that our type T is different than the head H. So we can use a type class provided by Shapeless. This is the funny thing here. And it just tells us that the first type doesn't extend the second one. So in this case, we can define types being different as none of them extends the second one. So that are the first two implicits. And the last, third implicit is the recursive condition. So we require that also our type T is not present in the tail of this list. So we can check how it works in an example. So we have a function addUnique, which takes two parameters, an input list in, upper bounded by HList, of course, and the type T. And it is going to add the element of type T to this list in, but implicitly it requires that the type T is not yet present in the input list. So if we have an HList with int and string, it will be valid and it will compile if we, for example, want to add a boolean to this list. So it is okay. But if we want to add a second int, the code will not compile because the condition is not fulfilled. So let's take a look how compiler is looking for the implicits in this case. So to check that this application is valid, compiler has to exactly find this implicit. So not in, parameterized with the type we are going to add, so boolean, and the whole type of our HList. So first, of course, it will find the implicit definition for non-empty list. So it will compare that type boolean is different than the head. It is okay. So now it also has to find recursively that the type boolean is also not present in the tail of this list. So it hasn't proven the first thing yet. First, it has to find another implicit recursively. So now it is looking for a type not in with boolean and an HList with string. So this is one step deeper in the recursion. So now, of course, it is using the same implicit definition for non-empty lists. So first, it is checking that boolean is different than the head, and it is true. So once again, it has to recursively find an implicit for our type boolean and the empty list, which is, of course, true for any type. This was the first basic definition for empty lists. So compiler is able to immediately prove this one. And now it just goes back in the recursive lookup. So after that, it also was able to prove the second one. And finally, also the first one, so the original one it was looking for. So it makes this line of code valid, and it will compile. So basically, we can see that we are just using some type classes in Shapeless to provide us additional information about our types. And we define them for HList in recursive way. So we often have a couple of functions, and first is just for the empty list. This is the basic condition. And the more generic case is also for non-empty list. So this is just the general recursive definition. And to understand, we just have to think how the compiler is going recursively through our HList. And this type not in here was quite simple and trivial here, as it didn't even have any method, so it didn't do so much for us. So usually some type classes should provide us some additional behavior. So as an example of this, we can take a look at remove all method. So basically, an HList has this method, which can be called with another HList of some types we are going to remove from this HList. So here we have a list with int, string, and a list, and we are going to remove one string and one int. So compiler basically is able to filter out those two types from the list and can return us a pair of the removed elements and the rest of the list, which is just untouched, just the rest. So this is how the method is defined. So we require an instance of type class remove all, which is parameterized with two types of lists. And it tells us that from the first list, we are able to remove elements types from the second list. So this not only, of course, provides us this information, but it also tells us how to exactly do it. So it gives us just an apply method, which can take the one list and give us an output. So the out type is not very essential here. The point is that this type class provides us the real behavior of removing elements from an HList. Okay, so my case of the dependency injection problem was a case for applying Shapeless. You could see there was some problem with code application, and also the type seemed to be the clue to this issue, so the types diversity were the problem. And finally, it turned out that we were able to reflect the problem, our dependencies, as HList, and it allowed to implement a generic and type level solution. Okay, so now just a recap. So this is once again how the solution looked like. So we have first a set of dependencies which are just purely functional. There are two types, future dependency and actor dependency, and then we can use them to build our actor. So first we are defining what our actor needs, and then what dependencies we are providing. So the dependencies are declarative and functional, and this is just how we can simply define dynamic dependencies which are asynchronous, so that might be actors or just futures. Then, of course, the dependencies are composed by type, so this is type-driven. So while building the dependencies, the DSL is looking at the types and combines and binds the dependency with the types provided earlier. And of course, during this composition, during building the dependencies, the solution is able also to construct the execution flow for our futures so that automatically the futures will be run in a more efficient way for us as opposed to for comprehension. Okay, and of course, it is checking the dependencies in compile time. So if our actor requires some attributes, some types, then we will be sure that if our code compiles, then we provide the proper dependencies. So there will be nothing more like missing dependencies in runtime. Yeah, and finally, we were able to get rid of lots of boilerplate code. So instead of long wall of configuration steps for an actor, we can just implement the actor logic in an explicit way. Okay, this solution is available on my GitHub, so you can take a look. It is also published as an experimental library, so you can try it, and if you'd like, please comment or ask for anything. And that's all. Thank you.
Just 2 questions. We have very short time.
So this library is for akka and for props. Have you considered trying to make something more general, like for constructors, for general object constructors?
Yes, it's a good question. I was considering it. My first need was just for akka, but yeah, now I'm considering to extract something more generic. First, maybe for futures, but it can be also generic for any kind of, let's say, even monad with, let's say, yeah, generally they may be different levels for this, but yeah, it would be a good idea to extract something more general also for other purposes.
Thank you.
Hi, I want to ask you, if I have 2 ints that I need them in the dependency injection, can I define them as 2 different times, for example, user ID and shop ID, and then use them in this matter, or will it break because both of them are actually ints?
Okay, so at this point now, you would have to wrap them yourself. So you would have to provide exactly different types. So you would need to use wrappers. I was considering something like typed tagging, something like this. But yeah, I'm not yet sure if this is desired and it is a good solution. But the best way would be to have, for example, all IDs typed. So it would be just best to try to have unique types. But yeah, there may be some situation where you really need the same types. Then maybe a kind of type tagging would be the solution.
Okay, so if you have other questions, just approach Grzegorz later.
Yeah, please ask.
Thank you.
Thank you.